Okay, in the previous section, we just talk about LC circuit, LC oscillation, but it is only a simplified case. In practically, a lossless system does not really exist. It's just like when you have a spring, it cannot swinging forever. And similarly for the LC circuit, there must be some losses in between. So, but actually we will still like to learn the LC oscillation because it is simple and it can be act as a beginning, so that we can understand the case with energy losses easier. So in order to modify the LC circuit model to match the practical case, so we add a resistor in series with the LC tank, so that the resistor will consume power, which makes the energy loss. So in this case, we have a circuit like this, RLC in series, and likewise we calculate the total electromagnetic energy U. Actually, U is exactly the same with the previous case. However, the energy is not conserved in this case. Actually, the energy is consumed by the resistor. The power consumption is I square R, so that du dt will be minus I square R, which is the power loss, or you can say the energy loss per unit time. So we can still take the derivative of U with respect to time, and finally we can get an expression like this. So actually this one doesn't need to take the derivative, but I would be cancelled, similar in the previous case. You will see this I will be a factor, so one of the I will be cancelled. So the only remaining term is Ri, and we also derive the whole equation by L. So we have R over L here. We have R over L here. You can double check it by yourself if you have any doubt. So it's still a second order ODE, but with the first order term here. So this is the term referring to the energy loss. So this is called the damped oscillation. And here we'll talk about the charge decay. In the previous case, the charge does not decay. The charge is Q times the cosine function. So it will just go up and go down forever. But in this case, the charge will decay. The Q and cosine is similar, except omega prime here. However, we also need to multiply an exponential term, and as long as RL are positive value, so that this minus R over 2L is a negative value, which means that this is an exponential function with a negative exponent, so it will generally look like this, exponentially decay. And we have to know that the frequency of this oscillation is not 1 over square root of LC anymore. It is slightly smaller than that, which will be this is 1 over LC minus this term. So this is still a positive value. This number, take the square, must be a positive. So we have 1 over LC minus this term, and then take the square root. So omega prime must be smaller than the original omega, which is this term. So using the potential method, actually we can also derive this equation. So so we say that this is V, and or VC, but actually we can write it as V, and this is VR, the voltage drop of the resistor VR, and this is VL. This is VL. So we have VL, VR, and VC, and according to the KVL, we have VL plus VR plus VC equals to 0. And actually the current, we call it I, because there is only one path in this loop, so the current going through the LRC are also I. So VL will be L di dt, and the voltage for the resistor will be simply R times I, which is the Ohm's law, and VC we can call it C. We can call it V. Equals 0. And actually, we also know that I will be C dV dt. So we take the derivative for this equation, and also we multiply it by C and take the derivative. Maybe I can write. Okay, so we multiply by C and also take the first derivative. The y-hand side is 0, so it's still a 0. So in this case, it will be LC, and then the second derivative of I, and then we have RC di dt, and then V is C. So this is C dV dt. So if this C is multiplied here, and also take this one, so it will finally become sorry. So it will finally become I. Equals to 0. Something like this. So let us multiply 1 over LC. So it will become d square I dt square plus R over L di dt plus 1 over LC I equals to 0. So we have the second order equation like this, and similarly for this one it has the q as the variable, but actually it is linear, so no matter v, vr, vl, I also satisfy this equation. And as long as we need to see, so we have the so actually we have the equation like this, di dt plus 1 over LC equals I equals to 0. So we need to solve this second order ODE. So we change the second derivative into s squared, and then the first derivative is s, and then the original I is 1. So the characteristic equation or the auxiliary equation is like this. So so there will be 3 cases for this characteristic equation. So we will have delta equals to b squared over 4ac, which is b square r over l square minus 4lc. But actually there will be 3 cases: delta larger than 0, equals to 0, or smaller than 0. But actually we will not really care about larger than 0's case. Larger than 0, it will be positive distinguished roots, which means that it will have a exponentially decay response. So it is not actually a oscillation. So we don't care about the delta larger than 0's case. And if delta equals to 0, which means that it's still not an oscillation case, because it was something like a plus bt multiplied by an exponential function, which minus S1t, something like this. So it's still an exponential function, which is not an oscillation. So the only case we consider is delta smaller than 0, which means that r squared over l squared minus 4 over lc smaller than 0. For this case, we have complex conjugate roots, which means that S will be R over 2L, which is minus B over 2A, and then plus or minus B squared over 4AC. B squared over 4AC, and as this one is smaller than 0, so that we'll write it as 4LC minus R squared over L squared. This one multiplied by J divided by 2, something like this. Then we can finally write it as minus R over 2L plus or minus J square root 1 over LC minus R squared over 4L squared. So we'll be able to know that this term will be something like referring to the term exponential to minus RT over 2L, RT over 2L, and this is the omega prime. So omega prime will be, this one is omega squared minus R over 2L square, and then take the square root. So this is omega prime, and which is exactly the same as this one, as this one. So finally, we will get that I is exponential to minus RT over 2L A cosine omega prime L plus B sine omega prime T. Or you can write it as the polar form, which will become capital I exponential to minus RT over 2L, and then cosine omega prime T plus or minus phi doesn't really matter. And I will be A squared plus B squared, and take the square root. So we have the solution like this. And if it's Q, then it will be capital Q. And likewise, let me talk about the analogy for the spring mass system. Similarly, we take it to be x equals to 0, and then this is the x-axis. So originally we have the mass from the spring according to the Hooke's law, which is F equals to kx. And here we also model the friction force. Friction force is minus B x dot. X dot is the first derivative of x, which is actually the velocity. So this really makes sense, because if the mass doesn't move, it shouldn't have any friction force. And this friction force is the magnitude of the friction force is proportional to the velocity, but in opposite direction. So it will be, this assumption will make sense. So in this case, we have F equals the total net force, which is this one is the force due to the spring, and then the friction force, and then according to Newton's second law of motion, which will be m, this is ma, which is mx double dot the second derivative of x. Second derivative of x, so that we can write it as m d2x dt2 plus b dx dt plus kx equals to 0. So we divide by m. We divide by m, so that we will have dx dt plus b over m dx dt plus k over m x equals to 0. We have a second order equation like this, which means that we will get the same form of a solution, but the only difference is we change R to be B, we change L to be M, change L to be M, and also LC will be K over M. So the answer will be similar. Other argument will be similar. We only need to make this kind of changes. So let's see an example. So a series RLC circuit has inductance L, C, R, and began to oscillate at time t equals to 0. So at what time at t will the amplitude of change of the charge oscillation in this circuit to be 50% of its initial value? Note that we don't know the initial value. We don't really need to know the initial value because it doesn't really matter what the initial value is. So the argument will be simple. So let me rewrite. So actually we have the expression for the Q like this: Q exponential to minus R t over 2L cosine omega prime t omega prime t. Here we will take phi equals to 0 because it tells you that it starts to oscillate at t equals to 0, and actually when phi equals to 0 and t equals to 0, this term will be 1, so it makes sense. If it is if phi is just say pi over 2, then cosine pi over 2 will be 0. So it doesn't really match the condition given by this question. So actually we don't really need to know about what Q is, and we also don't need to care about this term. The point here is that it asks you what is the charge oscillation in circuit to become 50% of this initial value, which means that originally at t equals to 0, this term is 1. So the point here is that we only care about the time t RT over 2L. Maybe we can say that T0 equals to 0.5, which is 50%, which is 50%. Okay, so we solve this algebraic equation. which will be R T0 2L equals to ln2. And so T0 will be 2L over R ln2. And we substitute the number in it. 2 times the inductor is 12 millihenry. And then R is 1.5 ohm. 1.5 ohm ln2. So it will become 11 millisecond. 11 millisecond. So the next follow-up question is how many oscillations are complete within this time. So we need to consider about the frequency or the period of this oscillation. So we know that omega prime is omega square minus R over 2L square, and then take the square root, something like this. And omega square is nothing but 1 over LC. 1 over LC minus R over 2L square. Take the square root. So we substitute numbers. L 12 times 10 to minus 3, and then C is 1.6 times 10 to minus 6 farad, and R is 1.5 over 2 times 12 times 10 to minus 3, and take the square of this term, and then take the square root of the whole expression. So the angular frequency of this oscillation will be 7.217 kilo radian per second. Something like this. So actually we should know that if capital T is the period, then omega prime times T will be 2 pi. Or if you use F prime equals to omega prime over 2 pi. Yeah, this is the frequency, and omega prime is the angular frequency. So F prime T will be 1. So we should know this. We should know this about the period and frequency, the relationship between them. So the number of oscillation in 11 millisecond will be 7.217 times 10 to 3 over 2 pi, which means that we need to divide 11 millisecond by the period, and the period is nothing but 2 pi over omega prime. 2 pi divided by this term. So we need to use 11 millisecond multiplied by 7.217 times 10 to 3 over 2 pi. So this will be the number of oscillation, which will be 12.6 times. 12.6 times. So 12 oscillation is complete, and you still have another 0.6 period. Okay, so next we talk about the phasor. Yeah, the phasor. So the first case is very simple. It is resistive flow. So first of all, let us look look at this circuit diagram. So we have a AC EMF. In the text, we call it alternating EMF, which is a sinusoidal voltage source series with a resistor, which is very simple. So in this case, the voltage drop on this resistor is nothing but this. So this is actually the same. The angular frequency of this source is omega d. So the phasor of the alternating potential can be defined like this. VR is and IR are the phasor of the voltage and the current. So we can write it as V equals IR. And actually, the time domain function, small vr, equals to the phasor times the cosine omega dt, and IR would be VR over R. So VR over R is nothing but IR. So because we have this expression, So this is the relationship between the time domain function and the phasor. So the impedance of the resistor can be written like this. It is nothing but R. And Z, the impedance, is actually a complex generalization of resistance. Okay. So next. It is capacitive load. In this case, it is a alternative EMF series with a capacitor. So so the voltage across the capacitor is still Vc or times cosine omega dt, and Vc is actually EM. So as long as we know that IC is CD Vc dt, so that we take the derivative, so that we have omega d, C, and Vc, and take the derivative of cosine function, which will be minus sine, and actually minus sine is cosine this argument plus pi over 2, which means that the phase for the voltage is at 0 degree, but the phase of the current will be shifted left by pi over 2, or 90 degree. And the impedance of the capacitor will be defined as 1 over j omega c. In the textbook, it is not written like this, but I think this will be a better expression. Otherwise, many things will go to very strange. And actually, impedance is a complex number, so there's no point that, not to define it as a complex number. So Z, which is the impedance of a capacitor, will be 1 over J omega C. So this is interesting because the impedance of a capacitor is not only related to the capacitance itself, but also related to the frequency. In this case, if it is omega D, then the impedance is 1 over J omega DC, something like this. And with this case, we will still have VC equals IC times ZZ. But here, IC but here, IC is not exactly IC cosine omega dt. It will be something like IC equals to the real part of IC exponential to J omega dt. So you can check it yourself. If you are interested in it, it will be something like this. Exponential to J omega dt, and you will need to use the expression exponential I theta is cosine theta plus J sine theta, the Euler's equation. So it will be something like this. And this is the impedance of a capacitor. So the next case is the inductive flow. So we have an AC voltage source in series with an inductor. So similarly, we have the E like this, and then in this case, if we assume, in this case, if we it will be a little bit strange. It should be because in this case, the final solution should be something like. In this case, we should make it something like this, pi over 2. Maybe if you ask about why it will be minus over 2, because finally we come up with plus pi over 2 here. But actually, VL should be this term and with the same phases, which means the phase should be 0. But here we have the phase to be pi over 2, so that we should minus it by pi over 2. So we also have minus pi over 2 for the current. So because the circuit is linear, we can shift the input like this. But if we just make it easier, then we assume IL to be capital IL, which is the phasor of the I, times the cosine, and then we know that VL equals LD IL dt, so that we take the derivative. So we have omega d IL times L, and then derivative of the cosine is minus sine. So that it will become omega d LIL cosine omega d t plus pi over 2. So in this case, uh, the impedance of an inductor can be defined as ZL equals J omega d L, or in order to match that, we can only write J omega L. We don't need this d here, but actually, if it is omega d for the source, then the impedance is J omega dL, and likewise, the impedance of an inductor is related to both the inductance and also the signal frequency. So in this case, we also have VL equals IL times CL. The main point for defining the phasor for the capacitor and inductor like this is we hope to get the expression just similar to the Ohm's law. So you can regard it as a generalized Ohm's law for which satisfy for R, C, and L. But this time, here is not only a resistance, this is now an impedance, which is a generalized resistance in the complex domain. So we have some sample problem to get familiar with it. So the first one is we have a resistor. Series with a sinusoidal source, operate at EM FD. So what is the VR of T, and what is the phasor? VR? So this one is easy. So VRT is nothing but 36.0 cosine 2 pi FD, which is 60.0 T. So it is 30.0 cosine 120 pi T volt. Don't forget the unit. And VR is only a number, which is 36.0 volt. So for part B, what are the current? IR and capital IR, the phasor of the current. So IR, capital IR will be VR over R, which is 36.0 over R is 200. So in this case, it is 0.18 ampere. And in this case, IRT is 0.18 cosine 120 pi T. ampere. Yeah. So for resistor, it is trivial. It is trivial because the voltage and current have the same phases. And next, it is a capacitor, capacitor C, in series with a sinusoidal source. So we have a C, same EM and same FD. So what is the VC and capital VC, the phasor, the phasor. So in this case, VC is nothing but 36.0 cosine 120 pi t, which is actually the same because VC is nothing but this E. So nothing changed, and VC is 36.0 volt. This is volt. Okay, so for the voltage, it is easy. And likewise, we calculate the IC of T and also the phasor, capital IC. So in this case, IC is VC over CC, which is J omega D C VC. Because ZC is 1 over J omega C. So, and in this case, the frequency is omega D. So, we have J, and omega D is 120 pi. C is 15 times 10 to minus 6 farad. And VC is 36.0. Let me check the answer. Uh, 36 times 15 point. Pi. Okay, so the answer is 0.203 J. 0.203 A. So which is a complex number. And in this case, ICT would be 0.203, okay, which is this one, and then cosine still omega dt. Omega d is 120 pi t, and this one J, you can regard it as J 0.203 is nothing but exponential to J pi over 2 times 0.203. So which is a complex number. The norm is 0.203. So we have 0.203 here. And then this is the phase. Positive pi over 2. So we have positive pi over 2 for the phase. Something like this. So so the unit is ampere. So this is the case for the capacitor. And here we also have the case for the inductor. So similarly, VL is nothing but 36.0 cosine 120 pi t V. So actually the same, and VL is 36.0 volt. 0 volt. And for part B, IL will be VL over CL, which is VL over J omega D L, which is 36.0 over J 120 pi. L is 230 times 10 to minus 3 Henry. And so this will become minus J 0.415. So when you change it into a polar form, the norm will be 0.415 exponential to minus J pi over 2. You can see like this. You have this number here. So the phase is actually pi over 2, minus pi over 2. So this is the polar form. So in this case, we can write that ILT is 0.415 cosine omega d 120 pi t minus pi over 2 A. So this is the phasor for the RLC, and